This is the last lesson in Unit 4, Probability Distributions. And we're just going to compare a couple probability distributions and sort of wrap things up. So let's start with an example. Compare and contrast the following probability distributions. Cutting 5 cards from a standard deck with replacement and counting the number of face cards. Dealing 5 cards from the same standard deck and counting the number of face cards. So dealing the same 5 cards at the same time. So that implies no replacement. So really what we're looking at is the difference between independent and dependent events. This one will be independent. And if it's independent, that means we use a binomial distribution. And this one would be dependent. Dependent, and therefore we're going to use hypergeometric. All right, so let's just create a probability distribution for each one of these based on, on the example. So 5 cards from a deck. So the parameters. First of all, the random variable is the number of face cards in each case. So if we make the first column here be random variable, it can go from 0 up to 5 face cards. So we are dealing out 5 cards. 0 of them could be face cards 1, 2, 3, 4, 5. So that's our random variable. How many face cards are there? Then these other 2 columns are for our different probabilities. So let's make the middle column be for the binomial distribution for the independent, the first thing. So we just want P at X for that. We're also going to get P at X in this column, but that will be the hypergeometric distribution situation. So the parameters for the binomial one, we need to know X, of course, but we also need to know N, which is the number of trials. 5 cards dealt means 5 trials. P is the probability of success. There are 12 face cards in a deck out of 52. We can reduce that to 3 over 13. Q is the probability of failure. It's always equal to 1 minus P. So 1 minus 3 over 13 equals 10 over 13. Those are our parameters for the binomial distribution. So the probability of getting 0 face cards with replacement is going to be 5 choose 0, n choose x, times p to the x, p is though 3 over 13, and x again is 0, and then times q to the x. Q is 10 over 13. And that's to the exponent 5 to the n minus x. When I work that out, I get 0.269. I'll just squeeze that in underneath here. And that's the probability of getting 0 face cards with replacement. If I do it again, I'll just do one more. The probability of getting 1 face card, well, now this 0 changes to a 1. And this 0 changes to a 1, and this 5 changes to a 4. And the probability of working all that out is equal to 0.404. So from that we can already see there's a higher probability of getting 1 face card than 0 face cards in this situation. I won't work out each one of the rest of them. Here you get the idea. For 2, it would be, getting 2 face cards would be 0.242. For getting 3, it's 0.073. 4 face cards, probability of that, you notice the probability is going down, it's down to about 1%. And the probability of getting 5 face cards out of all 5 cards is about 1 tenth of 1%, so 0.001. All right, so there's our distribution for with replacement, so independent binomial. Here's the parameters over here for hypergeometric. Now we have different variables. Our number of trials is represented by R in this case. So that's a cause of confusion, or possible cause of confusion. In binomial distributions, the number of trials is N. In hypergeometric distributions, the number of trials is represented by R. We do use N again, but now N is just the number of possible outcomes. And so each outcome, there's 52 outcomes to start with, 52 cards in a deck, so N is 52. And our other variable was A. A is the number of successes within those 52 outcomes. And then we put that together to get our distribution. And so again, let's just do the first one. When x is 0, then we have 12 successes. We want to choose 0 of them. And then we have 40 non-successes, 40 non-face cards. We want to get 5 of those. Over a total of 52 cards, then we're choosing 5 of them. And so once we have the numbers put in, it's pretty easy. It works out to be 253. So if you compare these two probabilities here, they're very similar. They're not the same, and that's the difference between replacement and not replacement, but they're similar. And then again, just to show for one card, so I have something to compare it to, we got 12 choose 1 times 40 choose 4 over always going to be 52 choose 5. And for this one, it's 0.422. And then again, to fill in the rest of them, just notice how these probabilities are close in each case to the hypergeometric ones. Sorry, the hypergeometric are close to the binomial ones, but they're not exactly the same. All right, if we want to graph each one of these probability distributions, then again we can make a histogram up. I'll just do that quick. And then having the different bars go to the different heights. So the bar for 0 would go to basically 0.27, so about here. And again, I'm just going to make the heights of the bars match up with the different probabilities. So this next one goes up to about slightly above 0.4, 0.24, 0.73, 0.11, and then basically the last bar is just going to be indistinguishable from that x-axis. So here is the distribution for binomial. I'll label that in a second, but this is the binomial distribution histogram. Here's the one for hypergeometric. So again, I'm going to go from 0.1 to 0.4 as far as the probability goes. And again, the last two bars, very low. Quick coloring in. There we go. The two probability distributions really similar. They both have that right skewed shape to them. Alright. So again, just connecting the tops of each of these bars. They both have a tail on the right hand side. So both right skewed. You know, there's some slight difference to the actual probabilities, but they are very similar. So the only other thing that I really need to do is just give you guys a summary of what we've looked at. So here's the uniform one. Well, we got uniform, binomial, and hypergeometric across the top. Those are the three specific types of probability distributions that we've looked at. They each have a formula that's unique to that type of distribution. So P at x in this case is just 1 over n. For the binomial one, it's n choose x times p to the x times q to the n minus x. And the probability for hypergeometric is a choose x times n minus a choose r minus x all over n choose r. The parameters and what they represent. So in this, again, let's go back to uniform. The only parameter really that we need to know is the population size. For binomial distribution, we had a few. We've already talked about it. We used it in the last example. N is the number of trials. P is the probability of success. And Q is probability of failure. Hypergeometric, N now stands for population size again, just like it did for the uniform distribution. Now R is the number of trials. A is the number of successes in a population. The definition of the random variable. What is a random variable representing? Well, in a uniform distribution, the random variable is the individual outcomes. Whereas for both binomial and hypergeometric, they are the number of successes. The range of values for x, for a uniform distribution, the range of values goes from 0 up to n. And that is likewise the range of values that we can have for the binomial distribution. Remember, again, n is the number of trials, so anywhere from 0 up to the number of trials. In hypergeometric, the number of trials is r, so that means that we change our range of values and go from 0 up to r in this case. Again, we can't have an x value that is greater than the number of trials. Think about the number of cards we pulled. If we pulled 5 cards from a deck and we're looking for the number of face cards, well, we couldn't have anything more than 5 face cards, logically speaking. So that's what this is telling us. The expectation formula, just thinking back, we haven't used that today, but we had a specific expectation formula for each of these specific different types of distributions. So for the uniform one, it was 1 over n times x1 plus x2 plus x3, because they were all the same, right? You just had to know what the values of these different things are, up to x sub n. For a binomial distribution, it's just n times p, so a number of trials times the probability of success. For a hypergeometric distribution, it was number of trials r times number of possible successes divided by n. And finally, the identifying characteristics. In a uniform distribution, we're always just talking about a single trial. Right? It's the only one where we're looking at doing one trial at a time, and they all have identical probabilities. For a binomial one, we have multiple trials. But the key identifier for that is independent outcomes. And the last one is also multiple trials, but this time we have dependent outcomes. And that would be it for Unit 4.